Welcome to Growing Worlds, the podcast where we explore the science of exoplanets through conversation with early career researchers on the front line of discovery. I'm Lorenzo.
And I'm Jeni. In each episode, we meet a guest who takes us behind the science of planets, stars, and the search for life in the universe.
Today, we focus on the stars that host planets. Because if we want to know a planet's size and composition and even its potential for life, we first need to understand its star.
And to help us navigate this stellar side of exoplanet science, we're joined by Dr. Gael Buldgen from the University of Liège. Gael, welcome to Growing Worlds.
Thanks a lot for having me.
We're very happy to have you. Thank you for coming on the show.
Gael is a postdoctoral researcher at the University of Liège, where he works on detailed characterization of stars, which is the very foundation of our understanding of exoplanet. He specializes in asteroseismology, which is the study of stellar oscillations, which allows scientists to probe the internal structure of stars with exquisite precision. It's a bit like doing an ultrasound on stellar interior. Through this, Gael's refined key stellar parameters such as mass, radius, and age, which impact directly how we interpret the properties of orbiting planets. He also contributed to missions like Kepler, TESS, and is involved in preparing the ESA's Ariel and Plato missions to make sure that when we analyze exoplanet atmosphere, we truly understand the lights of the star that is behind it.
So, Gael, before we get into the science, right, we should talk about how you got into the science. So it's like your story, what drew you to study stars and to astronomy? Was it a particular moment in your life, or was it you were just always obsessed? What drove you into stellar physics?
So stellar physics itself, it started third bachelor year at the university. So I did a bachelor in physics. I was hesitating between physics and engineering. It was a very pragmatic choice. My brother is an engineer. And he's older than me. I didn't want to do the same as my brother, so I went into physics. So
You don't want to put all the eggs in the same place,
Exactly.
right?
So I did my bachelor in physics, and I did this. It was a small internship in the group of stellar physics in Liège, and I really liked it. So I liked the idea that you could, model what's happening inside a star, and the fact that there is a wide variety of physical processes happening there. You have the largest scales to the smallest scales. You have convective cells in the sun, for example, the size of Europe, and you're probing also atomic physics like to 10 to the minus 15 meters. So that's something that I was very interested into and got me into continuing in stellar physics. Then when I chose the master's, I just picked every course that had the word stellar in it. And we were lucky we had a lot of options, and I could continue and specialize. And then it became quite naturally. But the primary choice to do physics, I just didn't want to do the same as my brother. That was the primary choice.
Sibling rivalry. It's not that
Yeah.
I actually liked physics. I just wanted to get back at my brother. There we are.
Exactly. No, I mean, I think I would have liked physics anyway, but really the way I approach things, I guess it was much more happy doing physics the way I do now in research than being in a company or something like that. So I'm better off, I think. So it paid off in the
Yeah.
end, but it was a very pragmatic choice.
Yeah. Were you interested in astronomy like as a kid, or was it just kind of like when you got older and you were looking at university choices?
I
Just seemed like
always
a good
liked
option.
astronomy. I always liked astronomy. I mean, already as a kid, and I was just wandering around the internet looking at stuff, Also, I got interested in space missions really early, but I didn't know whether I would go on the engineering side, designing missions, trying to get into ESA or things like that, or going really more on the scientific side. I was very hesitant on these aspects, but at the end, I chose to go for the physics.
I think what's quite telling is that when you said you were always looking at space, it wasn't you were out looking at the sky, you were looking on the internet.
Yeah.
And I think that is so telling that now that you've gone into theoretical, using computers, building models, it was there right from the beginning, that little seed.
So I really think that, the way that's also why I enjoy stellar physics itself, is because I see stars as laboratories. So that's why that's what I liked about that, is that, okay, like with seismology, we're going to probe the internal structure of a star, its dynamics. And at the end of the day, you're looking at dynamical processes and I end up talking to people doing, for example, opacity measurements or plasma physics or things like that. And so for me, it's really I'm kind of an experimentalist in the end. It's just that I use oscillations to do my experiments in a way.
I mean, to be fair, you can't put a star in a lab.
No.
A lot of people wish we could, but
No.
we
You
can't.
you can do a few tests in stellar conditions, but not many. And that's what makes still the stars very interesting, at least from a physical point of view. You have a lot of detailed physics you can test.
When we talk about characterizing exoplanet, we often hear about these light curves and retrievals. But behind all of this lies the star that you love and that you use as a lab. So can you put on your lab coat and walk us through how knowing this star properties like temperature, composition, or age is so fundamental in understanding the planets?
Yeah, so you have key thing with stars really is that they are opaque. So the first thing when you look at them, you only see it's like looking at a bowling ball. You only see the surface. So when we think about temperature is the surface temperature we see, or the luminosity is the total energy irradiated by the star. That's going to be very interesting for the planet because it's going to determine the amount of energy it's receiving. Then you have the chemical composition, where it can actually be, you see the surface chemical composition. It can help you constrain also the population in which the planetary system is formed, because you have to put your stellar models in perspective with the galactic evolution also. But really, for the age, you need to go inside. And that's where seismology really comes in. So for there, it's really, you mentioned doing an ultrasound. I like the analogy. What we do often as an analogy also is to say, because it's most of the oscillations we'll see at the surface of solar-like stars will be acoustic modes, it's pressure waves. So when I explain this to students, I say it's like you listen to a musical instrument and you try to reconstruct the musical instrument from the sound it makes. And that's what we do with stars in the end. And so you try to probe the internal structure of it and determine some key characteristics like how evolved is it, how much hydrogen remain in its core if you're looking at a main sequence star, for example, how massive is it? Because essentially it's the mean density of the star is going to determine the period of the oscillations, the dynamical time of the oscillations. And from there, you always kind of get the fundamental parameters, mass, radius, age, that you will need to characterize your exoplanetary system. Because if you do a transit, you get the size of the planet relative to that of the star. Radial velocities, well, it's the mass of the planet relative to that of the star. And when you see these, in exoplanetology, you plot often, the mass and radius diagram and things like that. And sure, but where is the time in this? How did these planets land in these positions? And they have evolved around the star and they've interacted with the star. How much atmosphere a planet will remain depends on how long it has been irradiated by the host star. So that's why when you look at Plato, for example, you have detailed objectives. We have requirements on how precisely we need to characterize the stars. And also for Ariel, you have a working group dedicated to that, actually, to seeing how far we can push the stellar models and how well we can characterize the stars.
There are two things I want like you to expand a little. First thing, in order of, as you said it, you mentioned that we need to put the star and the planets into the population where it formed. And you are not referring here, I guess, the planetary population in sense of the planets and all the other planets on the same orbit. You are talking about the stellar population. Am I right? How can this affect how the planets build? And before you dive into that, I also throw you the second question, which is, you mentioned, and this is fundamental for today's our topic, that you cannot have a measurement of the planets without measurement on the star. So can you walk us through a little how this determination of planetary mass and planetary radius with the two methods that you mentioned before?
So the population aspect, well, there is, as you know, in astrophysics, we kind of separate the elements. You have hydrogen, helium, and then all the other heavy elements, right?
We're not too picky, just the first two, and the other ones are just the other ones.
Yeah. It's hydrogen, helium, and metals.
Exactly.
You don't need anything
Exactly.
else.
The other ones are
the
metals.
periodic table is just
Exactly.
too complicated, frankly.
Exactly. So in this respect, you have, for example, the question of how much metals do you need to actually be able to form a system with terrestrial planets, for example. This is not going to be possible when you're looking at the first stars, because these will not have synthesized metals. All the heavier elements in the universe, I mean, heavier than helium, are synthesized in the core of stars. So you need the proper environment to be able to form your planets. So this is why some surveys that are looking at different populations, for example, of exoplanets are very interesting in that, to understand where they can actually form. Or if you think about environment like stellar clusters, how many planets do we know in stellar clusters? I wouldn't be able to answer that question, but we haven't looked at many of them. But if you imagine, if you're in the stellar clusters, you have all these stars forming together, a lot of interactions. How stable actually can planetary systems be? I don't know if we have an answer to that question yet. So that's why, for example, also analyzing the planetary populations, you have to think about it. If we want to understand the formation process, we need to look at a wide variety of stellar environments to understand how planets form, how they migrate actually in these conditions, depending how the protoplanetary disk will be last and how long it will last and things like that. So there is a lot of uncertainty in this. And that's where I think a lot of the synergies between, at least between stellar physics and exoplanetology, have not yet been fully exploited, perhaps, because there are lots of things still to be understood about stars and about stellar populations. The question was about transits and radial velocities, right?
Yes, the measurement of the planetary properties compared to the stars.
So essentially what you're looking at when you're looking at the transit method is you have your star and you have your planet passing in front of it, and you'll see a small dip in luminosity, because the planet is essentially just eclipsing a small portion of the stellar surface. So that dip in luminosity, of course, will be proportional to the size of the planet with respect to that of the star. And of course, the star is much bigger, much brighter. So that's why you have a lot of programs dedicated also looking at very small stars, like what we would call M dwarfs, because the transit depth then will be actually deeper because the star is less bright than, let's say, a red giant, for example. So that small dip will give you the relative size. If you know the size of your star, you have the radius of your planet. You're good.
How do you find the size of a star?
You have different methods. So for that, you need models, or if you're lucky, you have interferometry. So you can actually get the angular diameter from a star directly from interferometric measurement if it's close enough, if you can resolve the surface with
Isn't that
interferometers.
amazing? You can actually resolve nearby stars.
Exactly. Other option, if it's a binary system where you can actually see the motions of the star and have a detailed characterization, that helps a lot.
But if you can't do that, yeah.
Models, models. You're stuck with the models. You'll need to fit a
Okay.
model to your observations.
And what's in these models?
A lot of things. So you have to, if you have so in your stellar evolutionary models, usually you have to also keep in mind we're not modeling just the star at a given precise point in time, right? We're simulating its
Mm.
entire evolution. So you have to, it's like a kitchen recipe if you want. You have to decide what chemical mixture you're going to put in it, how much hydrogen, how much helium, how many metals, which will be dominated by oxygen, carbon, and nitrogen mostly. Then you have how you're going to treat turbulence in your model. What are the nuclear reactions you will choose? What transport of chemicals you will actually consider apart from turbulence. You can actually think about it. It's an interesting case, but in sun-like stars, effects like sedimentation actually play a key role. Like, say you have an oxygen atom in the outer layers of the sun, in the outer convective layers of the sun. It's heavier than its surroundings, so it's going to sink. It sinks very
Yeah.
slowly, but since it has billions of years to do so, it significantly influences the chemical stratification inside the star. So you have to take that
Wow.
into account in your models.
Yeah.
You need an equation of state for the plasma. You need to model the interaction between matter and light. So all what we would call opacity. So all of these have to be modeled, usually taken as standards from physics computations, like lab computations or theoretical computations. And then you have to do your entire simulations and you hope to reproduce your observations. So there's a lot
And
of,
then when you say reproduce the observations, so this is things like you can observe how bright a star
yeah,
is, for example. And so
yeah,
it's like if the model can reproduce that luminosity, well,
yeah.
then the radius that it's telling you is probably pretty accurate.
You're going to try to have, usually for the radius, if you think about it, you're going to try to get, so the thing you're going to get is the surface chemical composition from spectroscopy. So that's
Okay.
what you're going to try to at least have that. If you
Have
do,
that
if
correct from the
have
model.
that correct, and then you're going to have the luminosity, the surface temperature. And those would be, I would say, now there are lots of people, we're still doing that a lot, but these are, I would say, the weak constraints. But then the interesting case is when you can actually have oscillations. When you detect the pulsation modes, so observationally, if you look at a solar, you just, I mean, to detect observation from solar-like stars is just a photometry. You just point your telescope, you look for a significant amount of time. For Kepler, it was 4 years, for example. You do the Fourier transform of that. You look at the time series, and you'll have peaks. It's going to be a comb-like structure. Like, you're going to see the peaks of the
That's
modes
amazing.
regularly spaced. And then you're going to try to reproduce that. So you have your evolutionary model, and the question is
Yeah.
it going to reproduce the music you're seeing? So you're going to simulate the oscillations.
Reproduce the music of the stars. I love that. So I love, so like Kepler stared at these stars for sort of 4 years.
Yeah,
Because it stared,
continuously. Yeah,
it gives you that baseline to then put it from a time series into
yeah,
frequency space.
yeah,
And then look for the frequencies
yeah,
which stand out. And then that gives you the vibrational
yeah,
modes. And if the
exactly.
model gives you those vibrational modes, you're like, yes,
The
we know
structure
how
should
big
be
this star
good.
is. And
The structure should be
yeah.
good enough. And to put this into perspective, right? You're gonna think, oh, Kepler is amazing. We've done that for 4 years. For the sun, we've been doing that for 30 years. So the data
Oh my
set you
goodness, have we
have there,
actually
yeah,
been staring at the sun
yes,
continuously
yes.
for
If
30
you look at
years?
it's been launched. Was it 1996? And it's still going. So the time
It's
series
just
there
been,
are insane.
yeah. And I guess because the sun is so close, you can maybe sense modes which you can't detect,
Exactly,
maybe on other stars just because of distance and the
exactly.
signals aren't strong enough. And right.
You have something that we call geometric cancellation. So for the sun, you see the surface. To describe the oscillation modes, you actually will have, you can detect them in velocity, also in spectroscopy. You'll have one region that will go towards you, one region that will go under, or you actually have these pressure variations. So mathematically, they would be described by what we call spherical harmonics that people doing quantum mechanics have seen a lot. And essentially, if you think about it, if you have a mode that has a lot of these oscillations, up, downs, up, downs, up, downs at the surface, when you don't see the surface of the star, you're going to have cancellation. You see,
Mm,
you're going to do the sum of all
yes,
these parts, you're not going to see it. So you only
of
see what we will
course.
call the low degree modes. And to put that into perspective for other stars than the sun, we see all the 0, 1, 2, or degree 0, 1, 2, sometimes 3. For the sun,
Hmm.
we go up to 1000.
Oh my
Wow.
goodness. So you can sort of see the sun
You do
vibrating
whatever
on
you
like the
want with the sun.
tiniest. Yeah.
And
Wow.
how good are our models of the sun by now then?
That's a good question. The models of the sun, I can tell you that's why also we are a bit confident when we provide the age of a star. For the sun, we can really do a full tomography of its structure and dynamics. And we see that the models reproduce the internal structure down to something like the worst disagreement we have is in one specific region of the structure of the sun. It's about 1.5%.
The worst.
The worst.
1.5% is the worst.
And
Yeah.
we're obsessing about that, but they're very,
It's
very
very
accurate.
accurate.
Yeah.
Yeah. So how do the different structures inside the sun sort of manifest in these vibrations, so that you're detecting through doing the astroseismology?
So if you think about the sound waves, right, they're going to be sensitive to local sound speed. It's like if you think about the sound
Okay.
propagating into a medium, it's going to be the frequency is going to change, or the path is going to change depending on the local sound speed, and that's exactly what you have inside a star. So the first thing that's going to manifest itself is the way the sound speed is changing inside the sun or the star. So it's essentially pressure over density, or temperature divided by chemical composition. And that's how you can actually directly then probe, for example,
Okay.
the conditions in the thermodynamical conditions in the plasma. So you can check it out if you go on Google, you look sound speed profile inside the sun, and then you'll see actually the profile measured
Okay. Yeah.
from a model, measured,
No, but actually,
actually
that's
measured.
wild. Isn't that wild?
It
And
is.
so then when the sound speed changes, that then tells you, okay, now the plasma is structured like this and it's structured like that.
Yeah.
and then you get your different layers. So
So
do you want to take us from the core of the sun
yeah, sure,
out?
sure. So in the core of the sun, what you have is essentially the nuclear reactions occurring. So you have the proton-proton chain, so hydrogen being fused into helium, and essentially that you have a quite high sound speed there. The medium is quite dense actually, and then it decreases, and in you have to imagine 98%, not 97% of the mass of the sun, 97% of the mass of the sun, the energy is transported by high energy radiations. Right? The sun is a big nuclear reactor. You have energy being produced in the core, you need to transport it outwards. So you have a decrease in sound speed as you're moving out from the core.
So how much of the core is the sun, like a percentage? Is the core like 10%
In
of the
radius,
radius
it's
of
going
the
to be
sun?
about between 20 and 25%.
20
Yeah,
and 25%. So
of
you've
the
got
core.
all your nuclear reactions going on in
Yeah,
that
yeah. They
20%.
increase relatively sharply in temperature. The efficiency of the nuclear reactions. So you can actually see that. You see the change of hydrogen inside the sun. So, like I told you before, we have the disagreements down to 1.5%, right? Worst case scenario, 1.5%. That's the disagreement. The uncertainty we have on that, I think, is 10 to the minus 5.
Basically, well, that in astronomy, there's no uncertainty. We know what is happening in the sun. So is it, because you were saying how it like will drop off in the core. So is there kind of like, because of the temperature change? So is that like there's right in the middle of that 20% is there's loads and loads of nuclear reactions, and then it's still happening in the core, but as you get further out in the core, it drops off.
Yeah, exactly. The efficiency of the nuclear reactions drops as you're moving out. And then you can,
Hmm.
what you can actually map, what you can actually have a very good trace of is the switch. So I told you 97% the energy is transported outwards by radiation. And then at some point it's turbulence taking over, right? The outer layers of the sun are convective.
And that's where we've got physical motion, so convection. It's like boiling water.
Exactly. So the position of where that happens, we have it down to 1 per 1,000 in radius.
Like, that's just what you just know
We know
exactly
because
where it
we know that
happens.
seat
And
full
because
mark.
the waves will actually see a change, when the modes will
Mm,
propagate, they will actually see this change in energy transport, and they will give you that
yeah.
precision, that location extremely precisely.
Wow.
And so we have been able to do this for the sun. We have been able to do that for some stars.
Ah, that's amazing. And have we found that with the stars that we've been able to do it for, that it's quite similar as in terms of as to what we find in the sun?
Not always. That's the interesting take. So not always. Like we have the models for the sun work very well. And I always tell when I have students, the sun is a very controlled environment because if you think about it, the mass of the sun, we know it very well. It's not from the models. The radius also.
Yeah,
The age
because we
also
can
is, but it's from the
we can
meteorites. We
measure.
know it from the meteorites. We
Yeah.
don't know it from stellar evolution. So when you
No, no, as
compute
an
a
actual
solar model,
measured.
exactly,
Yeah.
when you have to stop your model. So in a very controlled environment. But for other stars, we don't know. So the uncertainties then become much larger, actually. So that's why we can go from having this insane precision for the sun to, for example, I don't know, for a 1.6 solar mass star, for example, you can have a change of 20% in age in no time.
Uh, And that's only slightly bigger than the sun,
The problem is actually the changes in the nuclear reactions that are dominating inside the star. You go from the
even.
PP chain to the CNO cycle, which occurs in a turbulent zone, because you can understand this from a physical point of view. The temperature dependence of these nuclear reactions that are occurring in the more massive stars is much higher. So you have a lot of energy produced in a narrow range of temperature. You need to transport it outwards very efficiently. So radiation is not enough. So you have turbulence taking over. And when that happens, you actually have what we call in star evolution a convective core. You can look up, if you're interested, the literature on this. It's been a plague for stellar evolution for as long as stellar evolution has existed. And the problem is that you can change then very efficiently the amount of hydrogen you have for your star. So you can have something that looks, I mean, you don't know exactly how much hydrogen the star can burn because it can be
It's mixing, yeah.
transported, and your mixing is not well reproduced in your models, and that leads to large uncertainties in age measurements. So this is why in this case, again, seismology can help in the sense that we can then map where these transitions occur. We can try to give extensions of these mixed regions to improve the ages. Otherwise, I mean, you don't know if it's a young exoplanetary system or an old exoplanetary system. You can have relatively wild effects. And if you think about the luminosity, for example, or the mass, if you have a massive star, the luminosity can change quite a bit. And also the way it changes over time changes drastically with mass. So that changes a lot, for example, the irradiation history of your planetary system.
Right.
And that
Okay.
can
Yeah.
have dire consequences for the
Yeah.
evolution.
Yeah. Because we like a stable star, stable planet, stable star.
Exactly.
You mentioned all these uncertainties and the fact that if you don't know the age, this affect the understanding of the planets. But you also mentioned before that all the measurements of the planets, the direct measurement like radius and mass, are depending on the stars, right? So do you want to expand for us the concept of how the uncertainties of these parameters can change our understanding of the planets?
So the direct effect for the radius, it's a direct relation. It's r squared. It's the surface, so that's clear. And for the mass, it's in your radial velocity measurement. So depending on the mass of the planet or the mass of the star, you'll see a different changes, in the way they orbit each other. And so what we measure when we measure what we call these radial velocities, it's like what you do in binary stars. You measure the relative motion of the star and the planet, or of the two stars. And so there directly you have a direct relation. It directly propagates. The uncertainty that you have on the planetary on the stellar mass will directly also propagate on the planetary mass. If you don't know the star, you don't know the planet. And it's an issue for Kepler, for example. Actually, we have a lot of planets detected with Kepler for which we don't have a good radial velocity follow-up. So the masses remain quite uncertain for some of the Kepler stars, actually, because you didn't have all the southern hemisphere high quality instruments that could do the follow up, because Kepler observed mostly in the north.
And so, if you're uncertain on things like how stable the star is and if its luminosity is changing and stuff, can that then impact how we think whether a planet could be habitable or not?
Yeah, definitely, because it's going to change. So the problem is that the luminosity of a star is going to evolve a lot, especially before it lands on the main sequence. Well, on the main sequence, it's relatively stable, but you have a direct relation between mass and luminosity. The higher the mass, the higher the luminosity. And so if a star is more luminous, it's going to give more energy to the planets. The planet is going to lose much more atmosphere. The habitable zone is going to be pushed out. And the problem also is with more massive stars, they tend to rotate faster also. And that leads also to more activity, so more high energy radiation. That is also bad for habitability, because when we think about habitability, again, you have to define it. It's not just one thing to be, in the region where you can have liquid water. If your star is ejecting, is doing coronal mass ejections like every now and then, it's
Yeah.
going to be a bit difficult.
Yeah. Yeah, yeah. It's like we get fun aurora, but because our star it only ejects comparatively the tiniest amount of stuff. It just kind of does a little puff. It's not screaming at
Yeah.
us every few days.
And it's the sun is a very quiet object. I mean, and already, if you think about it, if you can have a massive event, like if you think about the Carrington event, where you had all the electronics. I mean, at that time there were not electronics, but I think you had. I remember with the event
Telegraph system.
exactly that were actually reactivated at some point, although they had been disconnected, but they were actually transmitting again just because of the event.
Yeah.
Yeah, you have to be. I mean, we don't necessarily realize how actually dependent on the star we are. You can have actually planes deviating their routes because of solar activity. So if you think about that, and people tell you, oh, the sun is a quiet star. Okay, but how quiet? Well, very quiet compared to other objects, and
Yeah. Yeah.
that can change a lot the evolution of the system, the habitability, but also the evolution of the planetary system. Even if you have a planet that is in the habitable zone compared to its luminosity, if it has been strongly irradiated before, it can have lost a lot of its atmosphere.
Yeah. Yeah. And then that inhibits the chances for future
Exactly.
life. So do you think, you know, with our current understanding of planets, of course, it's somewhat limited in terms of, we're now moving into that era of exoplanet characterization over exoplanet discovery. But is our kind of characterization of exoplanets going to be significantly impacted by our lack of understanding of the stars that they're orbiting? What do you think is going to be the dominating factor, actually studying the planets themselves, or the fact that we don't really understand the stars that they're orbiting?
I think that there is merit to both, and I think that the best approach is actually to not isolate them. In the sense that the star can be influenced by the planets. You can actually have, if you have a star engulfing a planet, it can spin up a bit. It can lose mass.
Okay.
So it can have chemical peculiarities. So that's interesting also from a point of view of stellar evolution. And of course, you can have star-planet interactions. You can have tidal interactions, the planets migrating. You can have irradiation, as I mentioned before. If the planet is close enough, you can have magnetic interactions also. You can actually have, the reconnections between the lines and stuff like that. And will actually couple the evolution of both objects. What I'm very enthusiastic about is starting to have characterization of planetary atmospheres. That's something that is actually funny in a way because, okay, we're going to be able to relate the composition of the planets to the composition of the star. And that's going to improve a lot of understanding of the formation of the systems and understand how both actually influence each other. So for me, that's something that looks very interesting. But I would say that in this respect, I would not see, for example, like some people would say Plato is a stellar mission or Plato is a planetary mission. For me, it's both. Or Ariel, same. It's going to focus on exoplanets, but we're going to learn a ton of stuff about stars in this respect. And I think that we have to see both, and we have to understand that it's a coupled system. It's mutually evolving, and it's mutually influencing each other. And the sun is a very good example of that. Again, if we go back to what we kind of know, if I tell you, for example, that the way the solar system is formed is actually not influencing the outer layers of the sun, but the inner core. It's actually influencing the neutrino fluxes we see, because we told about seismology, but the nuclear reactions produce neutrinos. And the neutrino fluxes are influenced by the way the solar system formed.
Huh. That's
That's an interesting take, because it's completely unexpected. So you see, you can have surprises like that when you take into account planetary formation, and that's why it's important also for stellar physicists to take that into account. So that's where we're going to learn a lot, I think. If we do this synergetically, we're going to get the best of both worlds.
I like that.
Amazing. Before we wrap up, I want to ask you our signature question.
So we love this. It's always fun to end on.
If you had to choose one celestial body, which could be a star, a planet, or something else entirely that represents you, what would it be and why?
It's difficult to answer.
This is the question that's flummoxing you. We've thrown stellar models, planetary evolution, the insides of stars. This is the one that gets Gael.
Yeah, that's the one that throws me off. No, I would have to stick with the one I like the most, I think, which is the sun, because there's a lot of hidden stuff and there is a lot of fun parts in the sun that don't necessarily always look fun, but that are very, there's a lot of chaos going on. There is a lot of unknowns, and there is a lot of diversity in it, in the sense that you have a lot of various influences and various physical processes happening in there. And I think that's why I like the sun, and that's why I think the fact that you have I'm a person that pays attention to a lot of details, I think, and in the sun, that's what you have to do. So that's why I identify a lot with the sun, and why I match with the helioseismology and solar modeling.
Brilliant. I love that. Gael, the man who has more than meets the eye, just like the sun. Look at that. Thank you so much for illuminating how stars are far more than just background lights. They are the keys to unlocking the secrets of their planets.
Thank you very much for having me.
And thank you all, everyone, for listening, understanding worlds behind our own stars with understanding the stars that give them light. Join us next time as we explore another corner of the universe and the people bringing it closer.
Boom, one take.